All right, so you were supposed to fill out your notes. This really should be how much you've got. There's a couple things I'm going to have everybody make sure they add to the top. Those were the extra slides if you went through the slideshow. You might not have understood everything you were reading, but I'm glad you got it written down so that you can just listen a little bit more today. So just to run you through it, there were 3 different definitions of acids and bases that you needed to get written down. So the first one, you can call him Arrhenius or Arrhenius. I've heard it both ways. So, but it was this guy who came up with the idea that an acid is defined by the fact that it will split into this little H. Okay, it'll have an H that comes off, the proton. And then a base is defined as having a hydroxide ion part to it. Okay. Bronsted Lowry is 2 guys, and they came around and they covered the basis for some of our weaker bases. That sounded weird. But they considered things like this, like this guy, who doesn't have an OH, but it is a base. So their definition was just whether I am a hydrogen donor or a hydrogen acceptor, okay? And you will hear us say proton a lot more. Okay, so a proton donor or proton acceptor. And when we're saying proton, that's just talking about the hydrogen. That's getting kind of moved back and forth. So on your POGL, you guys had it more like this, right? We had HF, we put it into a beaker of water, back forth arrow. What was one of the products that we made from that? What did we make? Hydronium was one. What was the other thing that was made? Huh? If the H got tossed over, who's left over? The fluorine. Okay? So you had an ion. All right, so what this is showing you is this is the acid. He donated the proton, and this would have been considered a base to Bronsted Lowry. In this example, this was the base, this was the acid. So this one handed over its hydrogen to form this, okay? So we're gonna see that water kind of goes both ways. Then we had Lewis acid and bases. And with that, basically, this is covering things that maybe don't even have hydrogens in them, okay? And the way that I usually tell my AP to remember them is it's opposite of what you just wrote down for Bronsted Lowry, right? So now your acid is some sort of an acceptor and the base is a donor, okay? But we're talking about electron pair. So if you think about it, if for Bronsted Lowry it was donating a hydrogen, it accepts electrons in exchange for that, right? And so if you just think of it, they're kind of opposites. All that I'm gonna hold you guys to is just knowing what that definition is. So make sure you just keep those straight and you're studying them, okay? This does show you an example of something that doesn't typically look like an acid or a base, okay? But it's showing you that it falls under that definition, okay? All right, acids and bases have different properties. So for acids, they taste sour. Okay, so if you've ever heard of citric acid, that's in a lot of your candies, especially your sour candies. Okay, electrolytes. What does electrolyte mean? It means it conducts electricity. Yeah, that's fine. There's ions, right? So the minute you have ions, you are considered an electrolyte. Okay, so you have that plus or minus. The next one, litmus paper turns red. So litmus paper comes in either red or blue. If it's blue and I drop acid on it, it will turn red. If I have red litmus paper and I drop acid on it, it stays red. So no matter what, it's red. All right? So that's something that you do need to know these properties. So I'm going to give you a list of properties and ask you, is it an acid or base? And that's the way you're going to have to use it. I'm going to show you guys on Monday. All right. So metals react with acids to produce hydrogen gas. So where is this coming from? A metal kicking out hydrogen. What can you refer to that kind of shows that? Table. Which table? Everybody should have a periodic table. You're in chemistry class. The what?
I don't know how you explain it.
I thought you were saying it. Okay.
I said it.
No. Anybody got it?
Miss, is this line new?
Anybody got it?
Activity series.
It's your activity series. Good. No. Okay. It's your activity series. Oops. So I would add that in there so that you know that, because none of y'all got that. But activity series. If you look at your activity series, where's hydrogen at? Way at the bottom. Do you guys see that? You should be looking at an activity series. Okay, hydrogen is way at the bottom. All those metals on top of it can kick it out. So that's why if you drop a metal into some acid, you'll usually see bubbles, and those bubbles are the hydrogen gas. Okay? All right, it's going to react with a hydroxide to form salt and water. When I say salt, I am not necessarily talking about sodium chloride. I could be talking about any ionic compound out there. Okay, sodium chloride comes from sodium hydroxide mixing with hydrochloric acid, and that's it. Okay? All right, most formulas are going to have this H. If we can get to it today, we'll talk about how to calculate pH. But for acids, pHs are going to be from 0 to 7. Bases are going to be 7 to 14. So who do you think is at 7?
Weak acid. Strong.
Is it the 7 that you mix with your finger?
Water.
Oh.
Water, neutral water, right in the middle. Okay, and then everything kind of goes away from water. So the closer you are to 7, the more neutral you are, or the weaker you are. The further away you are, that means that you're going to have the higher concentrations of hydronium or hydroxides. Okay, and then we saw this in our POGL where it's producing the hydroniums. Bases, they produce hydroxides in water solutions. They have a bitter taste. So if you've ever eaten like kale or the dark chocolate and stuff like that, it's a bitter taste. Right, and that's kind of what kale is considered basic. Mm-hmm.
Basic.
It is basic salad. All right. So if you've ever gotten your mouth washed out with soap, anybody got lucky enough to do that? Yeah, me too. It's okay. Oh. We can all suffer together.
You were a good girl.
So that's also considered a base, and if you've ever had it happen to you, it's horrible and it's nasty. All right. So back on chemistry, it feels slippery. So that one, I'm not going to have you guys go and touch a bunch of the bases. Okay, you can't. But I can tell you from my experience, when I clean your guys' dishes after your labs, all your beakers and stuff, I can tell when we had sodium hydroxide because the beakers slip right out of my hands. They're very slippery. Okay, and acids definitely don't have that characteristic. All right. Reacts with acids to form salt and water. Hey, same thing, neutralization. This one turns the litmus paper blue. So this is probably the easier one to remember, blue base, base blue, okay? And so what this means is now if I have blue litmus paper and I drop base on it, it stays blue. If I have red litmus paper and I drop base on it, it turns blue, all right? So no matter what, your bases are going to turn this litmus indicator blue. Okay. The one that you guys are going to use for your lab is phenolphthalein, okay? And this one, it turns pink when it reaches the basic pH, meaning you're above 7. Acids will leave it clear, okay? So we're going to be using that when you guys do your titration lab. You contain hydroxides. They are also electrolytes. So do you think testing for conductivity is a good way to figure out if you have an acid or a base? No, because they're both electrolytes, so it doesn't help with anything. All right, and then pH is going to be greater than 7. All right, strong versus weak acids. So strong acids are the ones that completely ionize in solution. I think we have covered this pretty well, okay, in your POGL. So these are the ones that are going to completely break apart. They're electrolytes, they have ions, and weak acids are only going to partly ionize. So this is like 100% versus 20%. Okay? And that's the part that makes them a strong or weak, not concentration. Okay? Because if I ionize 100%, who did I just make a bunch of, by the way, for acids? Who did they make a bunch of? Hydroniums. Okay, and remember the goal for this is how many hydroniums can you create? All right. There are 7 common strong acids that you do need to kind of memorize. But I'm going to tell you right now, you don't have to memorize them. I'm going to give you a little saying that helps you memorize the... Actually, no, I'm going to do it right now. Just kidding.
Is it on the other side of the paper?
Yes, but write it on this side so you have it next to the bases. Because I'm going to show you 2 things to do. So if you do not have room because you wrote all over, you can use any of that bottom space. Save the top space for me for later.
Is it about that?
Okay?
Is it about buying?
Not yet. Okay, so, all right. So for these three, where do you guys notice these are coming from, by the way? They all have H's, but it's Cl, Br, I. Where are those guys found on your periodic table? Oh, they are part of the diatomic 7 as well, but yeah, I was going for halogens or the group 17, right? So you guys see that they're there. Who is missing from that little list?
Iodine. Wait, no, fluorine.
Fluorine, yeah. So do you guys remember back in the day when you don't need to draw this part. Remember we did that? Yeah. What was that? What was important about this corner? It was very, what was the word? Electronegative. It's very electronegative. So what that means is that it holds on for dear life. So what makes an acid strong? The fact that it does what? Split or stay together? Split. The class was split right down the middle. All right. It splits, right? We want to ionize. So if fluorine is super electronegative and holding on for dear life to that little hydrogen, is he going to let go of it? No. That's what makes fluorine with the hydrogen a little bit weaker than these guys. Okay? But the way you're going to remember these, you can write this. I bring clay. And then my AP always add in this part, not food. Because what that tells them is iodine, bromine, chlorine, not fluorine. Okay? So that's usually what they say. And so that helps you with the three main binary strong acids that you need to know. Okay, those are the strongs. This means so if I ask you, hey, hydrobromic acid, what's the percentage about that it ionizes? What's your answer? 100. 100 all the way, whatever. Is that what you said? Okay, that's fine. All right. So that's your binaries, okay? 100%. All right. Your ternaries or oxo acids have, what do you guys think? What do these all have? Well, they all have oxygen, but what are these things after the H's? What are those guys called? Polyatomics, okay? And so we're gonna go over naming next after we run through the rest of this. But the way to know if they're strong or not, if they have a polyatomic, is you have to ask yourself, so write this one down, 2 or more oxygens than hydrogens. Ooh, that's a big, there you go. Okay. 2 or more O's than H's. So we can check this real quick. So for HNO3, we have 3 oxygens, 1 H. What's 3 minus 1? 2. All right. For sulfuric, we have 4 oxygens, 2 hydrogens. 4 minus 2? 2. For this one, we have 3 minus 1? 2. And this one, we have 4 minus 1? 3. All right. So what we just proved here is that we have 2 or more oxygens than hydrogens. All right. And that's what makes them strong. Okay? Because, and you don't need to draw this part, you can just watch. This would be nitric acid right here, and he's a strong one. This is HNO3. Okay, where do you notice oxygen is in terms of this? Is he up in the top corner or is he down in the bottom corner? Top corner. So what is he doing? Pulling or pushing? Pulling really hard, okay? So all these oxygens are pulling this away. They are just like pulling everything like that. But this little hydrogen is just like sitting here. So is it really probably pretty easy to take that hydrogen off? Just like pluck them off? Oh yeah. And so he's going to float around and be like, okay, I guess I'll form a hydronium. All right? So the whole idea is that when I have more of those oxygens pulling away from it, it's like a tug-of-war game. It's totally not balanced. And those hydrogens are going to leave. If I have more hydrogens and the oxygens aren't as much, there's not as much of a pull. You're not really breaking this bond anymore. Okay? So it's all about that bond. Okay? Do I need you to be able to explain that to me? No, you just need to know this rule. I just wanted to show you why it works. Okay? Cool? So you guys wrote down your 2 things for strongs? Okay, and I bring clay, not food. Cool? Rock. All right, so strong bases, they do the same exact thing. They're going to dissociate 100%. Okay? There are 8 common ones. So the way that you're going to remember this, so either on the bottom or off on the side of this little square, draw yourself kind of a boxy B. Okay? And we're going to draw a little piece of your periodic table. Basically, you make this B using calcium, strontium, barium. You go over to cesium, rubidium, potassium, sodium, and lithium. Okay? Those 8 mixed with a hydroxide are your strong bases. If it is not part of that list, it's a weak base. So as long as you know your strongs, if it's not strong, it's weak. That's the way you know your weak ones. Okay? Huh? Okay. So look on your periodic table. Make sure you're going to be able to find that B.
Is that RI?
RB. Right here. RB. Rubidium. All right. So strong ones, these are them. Weak ones are anybody not on this list. And if you want to add this, NH3 is the most common weak one that you will for sure be asked about. Did I stress that you're going to for sure be asked about ammonia? Yes. All right, cool. That's a weak base. All right. Always ask about it. All right. Next, neutralization reaction. So this is a net ionic representing this reaction. So it's basically like a summary of what's going on. Okay, this right here always represents the main event. The main event of a neutralization is that you took a little acid thing with a little base thing and made a neutral thing. Okay, but if we look at what actually happened, we do have hydrobromic acid, potassium hydroxide. By the way, are these guys strong or weak?
Strong.
They're both strong, yeah, because I bring clay, and then K is part of the B. All right, so these are both strong. So we had a strong, and we're making water and an ionic salt. So this is an example of something that's not sodium chloride, okay? What type of reaction is this besides neutralization? This is a double replacement. That's really all that you're doing, okay? All right. All right. Conjugate acids and conjugate bases. All right. So basically, this goes really closely with your Bronsted Lowry definition. All right. Your Bronsted Lowry definition said that H's are basically handed over, and they're either donated or accepted, and then now you have new things on the other side of your yield sign. All right. So conjugate acid is always hooked up with the base. This is the part everyone screws up, so just make sure you keep this straight. Conjugate acids get hooked up with the base. Conjugate bases get hooked up with the acids. Okay?
Can you zoom in?
Okay, so down here below, it's just showing you an example. So, who is this, by the way? Who's NH3? Ammonia. Good, ammonia. All right, so we have ammonia. That's a base, okay? We have water. Water's going to act as an acid. So who is donating the H? The water or the base? Who's the donor? The water, your acid. All right, this is your acid, this is your base. Okay.
So water is always acid?
No, water can be either one. Okay, so this base, who does it look close, or who does it look most like, the NH4 or the OH? Who does it look like? Come on, you guys, match it up. Who does it look like?
See one more time?
Who does it look like? NH3 looks closer to what?
Oxygen, I had to know water.
NH3. I'm so confused.
All right, NH3 kind of looks like NH4. Do you agree?
Oh,
Okay, good. I just want to make
you're
sure.
talking about water.
I don't know. It's okay. All right. Anyway, so this is the base. So who is this? The conjugate acid. Okay. The acid looks a little bit closer to hydroxide. So this is the acid. It turns into a conjugate base. Okay. And I usually show mine bracketed up like that so that I know who's connected. Okay. And that's what I would do. Basically, your acid and base are always the before picture. Your conjugates are the after picture. Okay? Okay, got it? For the most part, you gotta study. Okay, so this is the part that I would make sure you have added at the top. And some of you guys didn't, so that's okay. Just add it now. But this part right here. Okay. Amphoteric. Amphoteric means that a substance can act as both an acid and a base. So the example that I want you guys for sure to recognize is going to be water. And we've seen now water donates an H. If it donates an H, what does it mean? What does it turn into?
A base.
Well, what base specifically? What?
OH.
Hydroxide, right? So if it donates an H, we're going to have OH left over. If it takes on an H, what does it become? If it takes on an H, if it accepts an H, hydronium, okay? So water is amphoteric. Water can either donate or accept. That's what the word means, amphoteric. Water. Do we got that? Did we write it down? Sweet. Okay. All right. Don't you write anything there? All right. The next thing I would like you to also add to the top, I would write that. And technically, you could say A or B. Okay? Except this will end up looking different because it'll be a base. But don't worry about that. Just write KA and then write that thing. We'll talk about it in a second. Write it down and then listen. All right, so K values, that's from an equilibrium thing, right? So it's our weak acids and bases will have K values. Okay, so how do we write K values? Who are these guys? Those are the products. These are the reactants. What is the reactant that's missing? Well, solids and liquids. So who is specifically, so this is like what we were doing yesterday. We had plus something.
Oh, water.
Yeah. You guys had H3O, I think, plus A minus. All right. So we're missing water. Will we ever have water in there? No, because it's liquid, right? Okay, so I just wanted to point out this is still the same thing that you guys are used to, just now you're going to usually have water and you never include it. So the bottom number tends, or the bottom part usually is only one thing. Okay? All right, so K value is not going away. Please write this statement down. Just that one. The larger the K, the stronger the acid. Same thing with the larger the K, the stronger the base. So no matter what, if I have a K value that is greater than 1, that means it's dissociating. It's going towards products. So you have a stronger acid or a stronger base. And I believe, I think so. I'm going to keep going. There's something else that I'm doing, but you can. Oh, no. Sorry. Write down this word. Just want to cover my bases, make sure we have everything. All right, polyprotic. What does poly mean? Many. And what does protic sound like? Protons. Okay, so what this means is many hydrogens. We call hydrogens that are moving in an acid-base thing, we call them protons. So if we have polyprotic acids, that would be something like H3PO4. This is a triprotic acid because it has 3 hydrogens. Okay? I just want to make sure you had that word because I know it shows up on one of your homeworks. So, protic. H2SO4 is also polyprotic. Yeah, so anything more than 1.
That's an acid.
H2SO4. This is phosphoric acid. Huh? It is weak. Good. Oh, that's right. I already went over that. I was like, how did you know that? That's awesome. All right. My bad. Did you guys hear that?
No.
By the way, this is a weak acid. You catch on to that? Because it's 4 minus 3, and 4 minus 3 is equal to what? 1. So that's not a strong acid. Doesn't it look like it should be a strong acid, though? Isn't it scary looking? It sounds scary. Phosphoric acid. And it's not. It's weak. All right.
What does it have to be to be a
2 or more oxygens than hydrogens. So you always subtract your oxygens minus your hydrogens. More than 2 or more oxygens. Yep. All right, cool. So, awesome. Turn your page over. You should have this on the back. I will try to make this short, sweet, simple. We already did the strongs, so that's cool. We already covered that part. But you have that reminder down there, just so you know. Right there. Okay. So, naming and formulas of acids. So, the reason there's a whole set of notes on this is because this is the part that takes the extra thinking. When you name bases, it's really easy. It's this. You go metal.
Should we write this?
Hydroxide. Yeah, write it in your corner. Right? So that's all it is for bases. Super easy. So that's why we're not even going to spend time doing notes on bases. You just put your metal, and then you use the word hydroxide. And who's the exception to that? You already forgot you already forgot this guy? Ammonium. Ammonia, sorry.
Ammonium?
No, ammonia. Ammonium is the one with 4.
So when it's just water, you say
It's its
water.
conjugate acid.
Right.
What?
It's water, you just say water.
Yeah. I've had people call it a hydrogen hydroxide. And I was like, that's cool. That's cool. I respect that. Because it can go either way. Or a hydrohydroxide, I think is what they say. And I'm like, okay. All right. Okay, so real quick. When you are naming acids, okay, you have 2 categories of acids. You have either binary or ternary. And I kind of went over this when we were talking about the strongs, okay? So your HCl, HBr, HI, those were all binary, meaning they only have 2 elements, okay? So 2 elements are present. There's one exception to this, of course, because chemistry. All right, yeah. So let's write it off to the side so that we make sure we don't mess that one up. HCN. CN is a polyatomic, it's on your chart under the polyatomics. That's cyanide, and we would call this the same way that we would call a binary acid. So we would say hydrocyanic acid. So you name it the same way that you would name a binary one. Okay? Because it's not technically an oxo acid, so it goes under the other category. All right, so binary ones, you'll see an H, and then you have another element. So the minute that you see that it's binary or you only have 2 elements present, you're going to start with the word hydro. So the minute you see hydro, this is very important. The minute you see hydro, you know that it's a binary. Okay? And you won't even bother with the rest of the stuff down there. So hydro, then you look at your anion, end with ic, and then you end with the word acid. So, for example, we have HF, 2 elements. I start with the word hydro. I look at who I'm talking about. It's fluorine. So I'm going to say fluoric, not fluorine. Huh? Hydrofluoric. And then acid. All right, the next one we have hydrobromic acid, right? By the way, hydrofluoric acid, is it strong or weak, you guys?
Strong.
Weak.
Weak.
What? It's broke.
Super electronegative. No, I bring clay, not food. Not food. No food. All right, okay?
So
Okay.
is that different?
All right. Hydroiodic acid. Okay, so let's just say, because you're obviously going to get both kind of examples. So I think going from the formula to the name isn't so bad. You'll get that. But you're going to look at this and be like, where do I start? Well, you notice that you have hydro first. So what that tells you is that I only have to do H and then see who this one kind of looks like. It says iotic, so that's... Yes, I thought that I wrote a plus sign right there, and I was like, why did I put a plus sign? But it was an H. It was just an ugly H. All right, so hydroiodic acid, okay? And then hydro, this should say chloric, by the way. Sorry. All right, so chloric acid, so this was HCl, right? So you saw the hydro. Got that part? Okay. When you notice that it is not just 2 elements and you have oxygens and polyatomics and all that stuff, you got to do an extra little step. So first of all, these are called ternary. They're also known as oxo acids. So they most likely have oxygen. They definitely involve polyatomics. Okay? All right. So first, you never include hydro. So the minute that you're looking at the names and you see, oh, it's not hydrochloric acid, it's just chloric acid, that tells you it's not HCl. That means that you got to go do these extra steps. So it says change the ending of your polyatomic ion. If you have a polyatomic ending with 8, you're going to end with ic. If you have a polyatomic with ite, you're going to end with aus. Okay? And then you're going to put, obviously, the word acid after that. All right, so everyone should have their chart open to polyatomics. Keep that right next to you because you're going to walk through these things so that you can see the steps. Okay? So open up your periodic table to your polyatomics. All right, this is a saying that'll help you remember which ones go together. Ich, I, eta, humongous, bite. So the ichs go with the polyatomics that end with any 8s, and the aus goes with anything that ends with ite. Okay, so that's the way to remember that one. And I'm just saying, somebody needs to make me a poster about that. I don't have one still. For extra credit for sure. Just saying.
I'm gonna make it before.
Is it just gonna be paper with the words on it? Or no? Okay. That'd be cool. All right. Okay. So sulfurous acid. So basically, if I were to give you just this part, and you had to come up with a name, okay? You would look at that and you'd say, oh, I see a polyatomic. Crap, that means I have to use that ich, I, eta, humongous, bite thing, right? So you're going to look at it and you're going to figure out who your polyatomic is. So you're given this. You understand that you have to look at this part. Who is SO3? Look it up. It's not sulfate. Sulfite. All right, so this is sulfite. So the minute I see this part, I know that ite makes it aus. So I would have sulfurous acid. Now, a common thing that always happens because you guys are first years is that you will put sulfus acid. You will, and it's okay. I will never count you wrong. I will nicely write it correctly, but nobody learns the ers and stuff like that until you've done chemistry over and over and over. So don't get mad at yourself if you forget the ers. All right? Sometimes they just add the ers in there. All right? It's sulfurous, not sulfus. Yeah. I promise you, everyone's going to mess up. Usually people mess up on phosphorus. That one's always a tough one. So just so you know, it's okay. All right. So let's just double check this one. We won't walk through all the steps necessarily, but this one we have SO4. Who is that? Sulfate. So ich, I, ate. So that means I need to end with ich, so sulfuric acid. There's that again. So if you said sulfic acid, I would say it's fine. I'll just nicely correct you.
Oh, ich's the person.
Okay, looking over here. I gotta make sure I get you guys to this. Okay, so for chloric acid, so we notice that there's no hydro. So that tells me that I have to use this funny little saying, okay? So the minute I see that there is no hydro, I'm like, okay, I gotta analyze my word. So first thing I should look at is the ending. It ends with ich. Ichs, I know, go with 8, okay? But then I have to look at this part and kind of figure out who I'm dealing with. So chlor kind of sounds like chlorine. So I know that there's going to be an H in the front because it's an acid. I know there's going to be a chlorine and some sort of an oxygen number. We just don't know what. So I have it set up, ready to go. Now I'm going to look up chlorate. So go look up chlorate in your list.
3.
Good. So it'll be ClO3. And what's the charge? A -1. The reason I'm asking that is because you have to crisscross charges again. I know. And some of you guys never learned it the first time. So now you got to really learn it. All right. Okay. So let me give you one more example. Even though we've already wrote it one time. But phosphoric acid. All right, so if I were to give you phosphoric acid, you would look at this and you would say, okay, it ends with ich, so that tells me it's a 8, okay? This is, kind of sounds like phosphorus, so I'm going to look up phosphate. Okay, I know that it's going to be an H. I know there's going to be a P and an O for sure. Just don't know what else is going to go with it. So look up phosphate. What is phosphate? PO4 with a charge of -3. So we're going to crisscross the charges. Okay, and that leaves us with H3PO4. So that's where our polyprotics come from, is the fact that they're mixed with things that have a charge. Okay. And that's kind of it for the note-taking part. I'm going to show you your next part real quick, and then we're done. So do you guys have any questions for me over naming? Okay. So just a heads up, the next page, this is a really good review. We will spend a little bit of time during class working on some of those, but I will not give you all the class time to do that. It might be a homework assignment next week, so if you're bored over the weekend, you're more than welcome to try some of these. Otherwise, I'm going to hand you the next worksheet, and I'm asking you to complete numbers 1 through 8 and 17 through 25. Okay? These are just naming your acids, what we just went over. Okay? And then decide if they're strong or weak. Okay?